Hey there, Shannon Myers, and today we're going to learn how to find a unit tangent vector at a point on a space curve and find the tangential and normal components of acceleration. Woohoo! So let's warm it on up by considering the two curves given by y1 equals 1 minus x squared and y2 equals x squared minus 1. So our first job is to find the unit tangent vectors to each curve at their points of intersection. So let's check it out. To find the point of intersection, we just equate them to each other. That's from earlier math. Always nice to bring that back in, isn't it? So here we go. 1 minus x squared, we set that equal to x squared minus 1. So let's see what'll happen. We'll get 2 is equal to 2x squared. So 1 is equal to x squared. And so x then would equal to plus or minus 1. Cool so far? All right. So here our points of intersection, therefore, are going to be why don't we go ahead and find them? So we'll have a point when x is positive 1, we will get 0 for y. And at x equal to negative 1, we will also get 0 for y because the x is squared. Groovy? All right, so now that we've found our points of intersection, we need to find, we're looking for tangent stuff, right? So we are going to want to differentiate, right? So we want to find d dx of y1 and d dx of y2. All right, so the first one, y1 was 1 minus x squared, right? So d dx of, all right, the y1 is equal to negative 2x, and then d dx of y2 is equal to, beautiful, positive 2x. Groovy? All right, so now we need to find unit tangent vectors, right? So working our way over here. So we need to find unit tangent vectors. So at x equal to positive 1, d dx of y1 is just going to be what? When x is positive, we're going to get negative 2 times 1, right? Which is negative 2. Cool so far? And so that means it's going to have a slope of negative 2, right? And so therefore we can let some u vector equal to 1, negative 2, right? That gives us a slope of negative 2. And u over the magnitude of u is going to be negative 2, and then 1 squared plus negative 2 squared under a square root gives us root 5. Cool so far? And so what we found is this is the unit vector tangent to y1, because we use the slope for y1. Now, continuing with the same point, 1, 0, when x equals to 1, right, we will, let me change colors here. So again, at x equal to 1, we're now going to take a look at d dx of y2, and that would end up being positive 2 times 1, which is 2. So you can call this one, I don't know, vector v, I guess. And so vector v has a slope of 2, so we can call that one 1, 2. And then vector v over the magnitude of vector v is equal to 1, 2 over, and again, aren't we going to have the square root of 5? Groovy? All right, perfect. So now let's take a look at, and this, again, both of so this vector now is a unit vector. Again, it's at the point 1, 0, but now it's tangent to y2. So continuing, let's see what we have going on. So at x equal to -1, d dx of y1 would now be -2 times -1, so we get a positive 2. So if we let some vector w equal to 1, 2, then w over the magnitude of w is equal to 1, 2 over root 5. Cool so far? All right, and then if we go, lastly, if we go up here and call this one, gosh, I don't know, vector, I don't want to call it R because we've been using R. Call it vector B, I don't know. So vector B, actually at x equal to -1, d dx of y2 is now going to be good, -2. So I think we decided to call this vector B, and we would have, that would be, we could say 1, -2. And then vector B over the magnitude of vector B is going to be equal to 1, -2, and again we get the same magnitude of root 5. Cool, cool? Okay, so, and this one here that we did just now, this one is tangent to, this is the unit vector, tangent to y2, and this one was the unit vector, tangent to y1. Cool, cool? Okay, so let's just get a visual of this going on. If we just do a quick sketch, this isn't a hard graph to do. So so if we've got the two graphs, so let's say that we've got the two graphs, so let's just graph this one in blue. So this is y1, and so here it's going to open downward and be shifted up by 1. And then we already know they both intersect at these points here. And then if I go over to 2, I think I'll be down at negative 3. So that's the first graph, the graph of y1. And then the graph of y2 we can do in, what color haven't we used? I guess we can do that one in green, y2. So that one's going to be shifted down 1, but it'll open upward. So again, we've got those intercepts, and then we'll have so it's going to look something like this. All right, 1 over root 5 is approximately 0.45. So graphing these unit tangent vectors, you're going to start at 1, 0, and we're going to be looking at first y1, the unit vector tangent to y1, and so that's going to be what, positive 0.45, and then from that point, and then negative 0.89, so it'll be about here, like this. Zoom in. It'll be about like that. Cool. And then the other one that's tangent to y1 was the pink one. Okay, now this is at x is negative 1. And so now it's going to be positive, right? So we're going to have, from that point, we're going to go up, or to the right 0.45-ish, and then up about 0.89. And so that's what that tangent vector will look like. Pretty cool, huh? Okay, and then similarly, we'll do the purple one next. This one's going to be at the point at x equal to negative 1, so 1, 0 again. And it's going to go, they're both going to be positive. So from 1, 0 over about 0.5, sorry, and then up. So it's going to look something like this. And then the last one is this kind of reddish pink one, and so it will be at x is negative 1, and it'll have positive movement on the x and negative movement on that, on the y, so it'll be something like this. Cool? So those are our tangent vectors, our unit tangent vectors at the 2 points. Cool. All right, so now what's our next job? Our next job is to find the angles where theta's between 0 and 90 degrees inclusive between the curves at their points of intersection. So here, okay, so one way to look at this is we're going to have, let's use black. So do you see this one seems to be greater than 90 degrees, right? So here, what we're going to be looking at is this here, right? This here. And so that would be our theta that we'd be looking for. Okay, so let's check it out. So find these angles between the curves at their points of intersection. So when we work on this one at 1, 0, so in general, we'll have cosine theta at this point is going to be equal to, let's see which two vectors. I named them all different things. So we would have at 1, 0, we'd have the purple vector and the blue vector, right? So we would have u dot v, that's what I had named them, over the magnitude of u times the magnitude of v, and that's just from the formula, right, for cosine, for the angle between two vectors. Groovy? All right, well, we already found the magnitude of u and v, right? So we would end up with cosine theta is equal to the dot product of 1, -2 dot 1, 2, and then over, we've already found those magnitudes, right? So it'd be √5 times, I won't do a dot, I'll say √5 times √5. Cool so far? All right, and again, I got these from over here. The purple vector was v, and the blue vector was u. So continuing, we will have cosine theta is equal to, what's that going to be? 1 times 1 plus -2 times 2, so I believe we'll get -3 fifths, -3 fifths. Now, when you find the inverse cosine of this, you're going to end up getting something which is in the second quadrant, remember? And we're looking for something between 0 and 90 degrees, so we're going to have to subtract our result from 180 degrees. So anyway, just go into our calculator. We would have make sure you're in degrees. And we had second arc cosine of -3 fifths, or -0.6. Enter. That's 126.9 approximately degrees. But remember, so theta is approximately 126.9 degrees, but we want theta to be between 0 and 90 degrees. So our actual theta we would need to find, and really, I guess, what we would need to do is we would need to go from that second quadrant minus, and then that gives us, I believe, 53.1 degrees. Cool? So I guess you could have put cosine alpha initially. That might have been more proper. And then found, since it was negative, so then you would find alpha, and then this one would be your theta. Groovy? Okay. So anyway, that's what we did. So we basically found the angle between, and they're symmetric, right? So the angle between the other two are going to be the same. So groovy? All right, so here we go. Next up we have our regular stuff. So let's take a look at the definition of a unit tangent vector. Let C be a smooth curve represented by the vector r on an open interval I. The unit tangent vector t at t is defined, well, t, that's kind of redundant. T at t is defined to be t at t equals r prime at t over the magnitude of r prime at t, where r prime at t, heard my kitty, is not equal to the zero vector. That's from the definition of a smooth curve. Okay. So the tangent line to a curve at a point is the line passing through the point and parallel to the unit tangent vector. Okay, so let's take a look at how we would find this, right? So find the unit tangent vector to the curve. R at t equals e to the t cosine t times I plus e to the tj when t is equal to 0. Well, we're going to need to find this stuff, right? We're going to need to find r prime at t, aren't we? So we'll start there. So r prime at t is going to be, good, we're going to need to use the product rule. So e to the t cosine t minus e to the t sine t times I, and then plus e to the t times j. Good so far? I'm going to go ahead and factor out, to make it easier to work with, I'm going to factor out an e to the t, and we can factor that out from the whole entire expression. And so then we would have cosine t minus sine t times I plus j. Groovy? Awesome. Now r prime, sorry, it's a vector, at 0, well, wherever there's a t, we're going to just plug in 0, right? So here we go. We'll get e to the 0 times cosine 0 minus sine 0 times all that times I, and then plus j. And so r prime at 0 will be e to the 0 is just 1, right? So we'll, and cosine at 0 is 1, sine at 0 is 0. So I believe we will just get I plus j at the end of the day. Groovy? All right, so now we found r prime at t, and so we need to find the magnitude of r prime at t. So the magnitude, actually not t, but 0, r prime at 0, is going to be the square root of 1 squared plus 1 squared, right? Because those were our coefficients to the I and j. And that's just going to equal to the square root of 2. Cool so far? And so, what did we find? Our tangent vector, our unit tangent vector to this curve at t equal to 0 is 1 over root 2 times the vector 1, 1. Or, in terms of I and j, we would have 1 over root 2 times I plus j. Cool, cool? And since it was given in terms of I and j, we'll go ahead and keep it in terms of that. All right. How's it going so far? Awesome. See, I knew you could do it. Okay, so next up, example 2, consider the space curve r at t equal to, this is in component form, t square root of 4 minus t squared at the point 1, 1, root 3. So part A, we need to find the unit tangent vector at the given point. All right, let's check out some steps. So let's think about it. 1, we got to find t, don't we? So to find t, what do we know? We know that x at t is equal to x1, right? Well, what was x at t? Beautiful. X at t was just t. That's from the first, that vector. And x1 from the point is 1. Y at t is equal to y1. And so, again, we just had t equal to 1. And then z at t is equal to the square root of 4 minus t squared. Okay. Z1. And what was z at t? It was the square root of 4 minus t squared, and that's got to equal to root 3. Cool so far? Awesome. So if I square both sides, I will get 4 minus t squared is 3, and then I would get 1 is equal to t squared, and then I would get plus or minus 1 is equal to t. But do you see how t was 1 for the other two? And so we're going to take that positive. Groovy? So t is equal to 1. Okay, so now, second up, we want to find r prime at t. So when we do this one, well, we know what x at t, y at t, and z at t are, and so the derivative of t with respect to t is going to be what? So we're going to have 1i plus 1j, because x at t and y at t were t. Now z at t was root 4 minus t squared. So we're going to end up getting plus negative 2t over 2 times the square root of 4 minus t squared times k. So cleaning that up, r prime at t will be I plus j minus t over the square root of 4 minus t squared times k. So thirdly, we want to find t at t and then t at 1. So remember that t at t is equal to r prime at t divided by the magnitude of r prime at t. So let's check it out. T at t will be, let's do this in component form. So we would have one negative t over the square root of 4 minus t squared, and then that's going to be over the magnitude of that, right? The magnitude of 1, and then negative t over the square root of 4 minus t squared. But since we don't need to keep this in general, why don't we go straight to t at 1? So that'll give us 1 negative 1 over root 3 over the magnitude of 1 negative 1 over root 3. So all I did was, wherever I saw a t, I put in a 1. Well, I did it in my head on that one. All right, so anyway, continuing, we will have t at 1 will equal to 1 negative 1 over root 3 over, let's see, the square root of 1 squared plus 1 squared plus 1/3. So 1 plus 1 plus 1/3. So t at 1 is equal to 1 negative 1 over root 3. And then that's going to be what? 7/3. So the square root of 7/3. So when you invert and multiply, I believe we would have t at 1 would be root 3 times 1 negative 1 over root 3 over root 7 and then we would get t at 1 is root 3 negative 1 all over root 7. If you rationalize, you'll get a slightly different looking response. But there you have it. We figured it out. Groovy? All right, so next up, we want to find a set of parametric equations for the line tangent to the space curve at the given point. Okay, so, and we're working with what we had, right? Our t at 1. So we know that t at 1 is equal to root 3, negative 1, all over root 7 from part A. So in this case, using direction cosines, right? Or not the direction cosines, the direction numbers, we would have A equal to root 3, B equal to root 3, and C equal to negative 1. And remember that x is equal to A times t plus x0. Y is equal to B times t plus y0, and z is equal to c times t plus z0. Well, we were given the point, weren't we? 1, 1, root 3. So this is going to give us x is equal to root 3 times t plus 1. Y is going to equal to root 3 times t plus 1. And z is going to equal to negative t plus root 3. Groovy? And that's not the only one you can get. If you rationalized, you'd have something different. And notice it says find a set of parametric equations. So we went ahead and we found this set here. We're good to go. All right. So next up we have definition. Principal unit normal vector. So let C be a smooth curve represented by R on an open interval I. If t prime at t is not equal to 0, then the principal unit normal vector n at t, sorry again redundancy, is defined to be n at t is equal to t prime at t over the magnitude of t prime at t. And remember in the last section, 12.3, we were looking at how the acceleration vector was always perpendicular to the velocity vector. So this is that same kind of idea. So at any point on a curve, a unit normal vector is orthogonal. That's the other way of saying perpendicular, right? Orthogonal to the unit tangent vector. The principal unit normal vector points in the direction in which the curve is turning. Okay, so that's something definitely to remember. So let's take a look at example 3. Find the principal unit normal vector to the curve R at t is natural log at t times I plus quantity t plus 1 times j at the time equal to 2. Okay, so what do we need to do? Well, why don't we find r prime at t first? Because aren't we going to need that to find t at t? So r prime at t, let's see, would be 1 over t times I plus 1j. Cool so far? The magnitude of r prime at t is going to equal to the square root of 1 over t, the quantity squared, plus 1 squared. So what's that going to end up giving us, you think? Not sure if it's going to be better. It's probably going to be better to simplify it a little bit. Maybe not, though. You know, honestly, I'm just going to keep it, I'm just going to write it as 1 over t squared plus 1. So that gives us that t at t is equal to, remember, r prime at t over the magnitude of r prime at t. So that's going to equal to 1 over t, and 1 in component form, over the square root of 1 over t squared plus 1. Groovy? We're probably going to want to go ahead and simplify this a bit because otherwise it's going to be rough to work with to get when we're differentiating t. So here, this will end up being, I'm going to write it like this, 1 over the square root of, if I get a common denominator, I would have t squared, I would have 1 plus t squared over t squared times 1 over t 1. That's going to give me t over 1 plus t squared to the 1/2 times 1 over t 1. And then if I bring that in, t times 1 over t, so I'll end up with 1 plus t squared to the negative 1/2. And then I'll end up with, over here, t over 1 plus t squared to the 1/2. So now I have to differentiate each of those, right? So to get t prime at t, I'll have, using the chain rule, negative 1/2 times our something to the negative 3/2 times the derivative of our something. So what's that something? It was 1 plus t squared. And then the derivative of that something is going to be times 2t. That takes care of the first component, right? So the derivative of the second component, I'll go ahead and just use the quotient rule. So we're going to end up getting 1 times 1 plus t squared to the 1/2 minus t times 1/2 times, I'll write it like this, 1/2 times 1 plus t squared to the negative 1/2 times 2t, again using the chain rule, all over 1 plus t squared the square root of 1 plus t squared squared. All right, so cleaning it up, we'll have t prime at t. We might need a couple iterations of cleaning here. Let's see, the 2's divide out. And so we're going to end up getting, for the first one, negative t over 1 plus t squared to the 3/2. Put it back in the denominator. And then for the second one, we're going to get, see, these 2's will divide out. And so we will have, we're going to factor out a 1 plus t squared to the negative 1/2. In the numerator, we'll be left with 1 plus t squared to the 1, right? That gets me to my 1/2. And then on this one, I'll have minus t squared. And then in the denominator, I'm going to have 1 plus t squared, because it was under a radical and that got squared. All right, so we're almost done with that part. T prime at t will be negative t over quantity 1 plus t squared to the 3/2, comma, that would give us 1 plus t squared minus t squared. So believe it or not, the numerator is just going to be 1. And then combining the denominators, we'll have, I believe, 1 plus t squared to the 3/2. That didn't turn out so bad, did it? All right. So now is where, for as far as the magnitude goes, I'm thinking that we can just evaluate. We can just find t prime at 2. Okay, so here, what's going to happen? N at 2 is going to be t prime at 2 over the magnitude of t prime at 2, right? So, well, what was t prime at 2? So if we do that, t prime at 2, so wherever there is a t, I'm going to plug in a 2, right? And so we don't know the magnitude yet. So t prime at 2 would give me what? Negative 2 over 5 to the 3/2. So negative 2 over 5 to the 3/2. And then 1 over 5 to the 3/2. over the square root of, now I'm going to square those, right? So when I square them, I believe we'll get 4 over, the square root will go away, so 4 over 5 cubed, right? Plus 1 over 5 cubed. So that's going to give us, let's see, 5 over 5 cubed, right? Which is 1 over 5 squared. So we will have 1 over the square root of 1 over 5 squared. Times negative 2 over 5 to the 3 halves, comma, 1 over 5 to the 3 halves. And we're almost done. The square root of 1 over 5 squared is a fifth, right? That 5 would jump up there. So we would have 5 to the 1, right, times negative 2 over 5 to the 3 halves, and then comma 1 over 5 to the 3 halves, and then in turn, sorry I'm working across like this, it's kind of sloppy, but then in turn what would happen? 5 to the, I'm doing 5 to the 1 divided by 5 to the 3 halves, so that would give me 5 to the negative a half. So basically I'll have 1 over root 5 and then negative 2 and 1. And so that's not horrible, right? And that's the final result. Cool, cool? Probably not. All right, so here we go. The acceleration vector. So if r at t is the position vector for a smooth curve C, and n at t exists, then the acceleration vector a at t is equal to a sub t, or that t is a vector, times t at t, and then plus a sub n times n at t lies in the plane determined by t at t and n at t. Okay, so for that one, so let's look at the proof for this one, okay? So if we do the proof, let's simplify the notation a little, right? We're going to let t at t just be equal to this t prime equal, whoops, be consistent here, t prime at t equal to this t prime vector, to also n at t equal to n. Okay, so here we go. Since t is equal to r prime at t over the magnitude of r prime at t, which equals to v over the magnitude of v, the velocity vector, right? It follows that what? If you take a look at that, at this part and this part, because they're all equated, right? We can say that v is equal to what? Good, the magnitude of v times t. Good so far? Awesome. So, by differentiating, what's going to happen? Because remember, a is, you differentiate a to get, or v to get a. So, let's see what happens. We get a is equal to v prime. So what we'll have here for v prime is we will have d dt, the magnitude of v times the t vector, plus the magnitude of v times t prime. That's just the product rule for derivatives. Now, if I go ahead and I were to multiply, so I'll just do a little trick, by the magnitude of t prime over the magnitude of t prime, so that last term, let's see what happens. We're going to end up with d dt of the magnitude of v times the vector t plus, and now we're going to have notice that t prime over t is going to be our n vector. T prime over the magnitude of t is going to be our n vector, isn't it? So we're going to have the magnitude of v times n times the magnitude of t prime. And where we got the n was because n is the vector t prime over the magnitude of the vector t prime. Cool so far? All right, so now let's think about a. We basically have a written as a linear combination of t and n, don't we? So what we can do is assume that a lies in the plane determined by t and n, letting a sub vector t equal to the coefficient in front of the t vector, so d dt of the magnitude of v, and a sub the n vector equal to the magnitude of v times the magnitude of t prime. We have the acceleration vector is equal to a sub t times the vector t plus a sub n times the principal unit normal vector. Groovy? And we're all done. All right, so tangential and normal components of acceleration. So for this one, if R at t is the position vector for a smooth curve C, and n at t exists, then the tangential and normal components of acceleration are as follows. So a sub t is equal to, this is just a different way of writing it, d with respect to t of the magnitude of the vector v, which is equal to, turns out, a dot t, the acceleration vector, dot the the unit tangent vector, and that's also equivalent to, v dot a over v, the magnitude of v. Okay. A sub n is equal to the magnitude of v times the magnitude of t prime at t, which in turn is equal to a dot n, which in turn is the magnitude of v cross a over the magnitude of v, which also happens to be equivalent to the magnitude of a squared minus a sub t squared. Note that a sub n is greater than or equal to 0. So the normal component of acceleration is also called the centripetal component of acceleration. Cool, cool? All right, so here we go. Let's look at the example. So find t at t, n at t, a sub t, a sub n for the plane curve r at t equals e to the ti plus e to the negative tj plus t times k at the time t equal to 0. Okay, so here we go. What do we need to find? We need to find, just so we know we're all squared away, what's x at t? X at t is, beautiful, e to the t. Y at t was e to the negative t, right? And z at t is equal to t. Cool so far? All right, now r prime at t is equal to, in component form, the vector e to the t, negative e to the negative t, and 1. Now, the magnitude of r prime at t in general is going to be the square root of e to the t squared plus e to the negative t squared plus 1 squared. But remember, when you raise a power to a power, what do you get? You can multiply. So we'll get the square root of e to the 2t plus e to the negative 2t plus 1. Now, if we were to get a common denominator, right, we would end up with e to the 4t plus 1 plus e to the 2t all over e to the 2t, which remember is equivalent to e to the t at quantity squared. So that's going to give us the square root of e to the 4t plus e to the 2t plus 1 all over e to the t. Cool so far? Okay, so now let's see what else we need to do. We found r prime, the magnitude of r prime, and so we can definitely find that allows us to find t, just t at time t. So that's going to, remember, be r prime at t over the magnitude of r prime at t. So that is going to equal to if I invert and multiply that magnitude, I would have e to the t as a coefficient in the numerator, and then I would end up with my e to the t, negative e to the negative t, and 1. And in the denominator, I would have my square root of e to the 4t plus e to the 2t plus 1, which would give me simplify it, if I, you know what, I'll bring that e to the t in, so we'll have e to the 2t, right? And then here we'd have e to the t times negative e to the negative t, so I believe we'll just get beautiful negative 1, and then e to the t all over the square root of e to the 4t plus e to the 2t plus 1. Cool so far? We're going to need to differentiate that to get our n at t. So take a deep breath. We're going to be working a little bit here. All right, so we wanted to find all of these things at t equal to 0, right? So here we can certainly take note that this was all, remember, t at t. Now, I'm going to copy this one because I'm sure we're going to need it. All right, so now t at 1 was one of the or t at 0 rather, was one of our jobs. So here, do you see that we would end up with e to the 2 times 0 is e to the 0. So we'd end up with 1, negative 1, 1 over 1 plus 1 plus 1 under the radical, so we'd have over root 3. Cool so far? So that was one of our jobs, was to find this one. Okay. Now, another job is we need to find some kind of mean looking stuff. So in order to find n, right, we're going to need to find each of these derivatives with that kind of mean-looking magnitude in general. So let's do it. So n at t t, remember, is t prime at t divided by the magnitude of t prime at t. Okay, so now t prime at t is basically going to be a few kind of mean expressions, right? So for our first component, so sorry about my dog. So first component, what are we going to have? So we have, it's really going to be e to the 2t divided by quantity e to the 4t plus e to the 2t plus 1 to the 1/2, right, for the first component, and we need to find ddt of this. Cool? So we're going to need to, I'll go ahead and I'll use the quotient rule. So we're going to get 2e to the 2t times e to the 4th plus 4t rather plus e to the 2t plus 1 raised to the 1/2 minus e to the 2t, and then using the chain rule, we're going to have 1/2 times e to the 4t plus e to the 2t plus 1 to the negative 1/2, and then times times 4e to the 4t plus 2e to the 2t. Sorry, it's squished in there. I'll zoom it. 4e to the 4t plus 2e to the 2t. Okay? And all of that is over the denominator squared. So that just gives us e to the 4t plus e to the 2t plus 1. Without it being a square root. Cool so far? I'm going to bring out a 1/2, okay, and e to the 2t, and then e to the 4t plus e to the 2t plus 1 to the negative 1/2, right? Because that's my smallest, my factor, the power that's most to the left. Now, to balance this out, we will have 4. This will be e to the 4t plus e to the 2t plus 1 raised to the 1 power to get me to the positive 1/2. And then I will have left minus 4e to the 4t plus 2e to the 2t. Cool? And now that'll be all over e to the 4t plus e to the 2t plus 1. Okay, now dropping down the that big trinomial that's to the negative 1/2, dropping it to the denominator. Let's see what I'm going to have. So I'm going to end up with 4e to the 4t. Now I'm distributing this. Plus 4e to the 2t plus 4 minus 4e to the 4t t minus 2e to the 2t all over 2 times quantity e to the 4t plus e to the 2t plus 1, and that'll now be to the 3/2. Cool so far? Well, fortunately, some of this stuff will zero out. The 4e to the 4t zero out, and we can combine a couple things. So let's see what we get. So we will have, this will equal to 2e to the 2t plus 4 over 2 times e to the 4t rather, plus e to the 2t plus 1 raised to the 3/2. Factoring out a 2 and then dividing out, we will get e to the 2t plus 2 over e to the 4t plus e to the 2t plus 1 raised to the 3/2. Cool so far? Oh, and I lost my e to the 2t, my bad. So that would be here. So we'd have e to the 2t. We'd have an e to the 2t. And then we'd have an e to the 2t here. Cool, cool? And that's the first component. Okay. The second component we'll do in a different color. So the second component, we'll do in green, I guess. So let's see, what was our second component will be easy because it was -1, right? So for the second component, we're going to have negative quantity e to the 4t plus e to the 2t plus 1 raised to the -1/2. That's our second component. And again, we're going to be finding the derivative with respect to t of this, but it's a heck of a lot easier than the last one. So that's going to end up being -1/2 times -1 is +1/2. And then we'll have e to the 4t plus e to the 2t plus 1, -3/2. And then we got to use the chain rule, so we'll get times 4e to the 4t plus 2e to the 2t. And then the 1 zeroes out. Cool, cool? Okay, so I can factor out a 2 from the numerator, that second factor. So I'll have 2e to the 4t plus e to the 2t over 2 times e to the 4t plus e to the 2t plus 1 raised to the 3/2. And those 2's will divide out, and so my second component, the derivative of that is going to end up being 2e to the 4t plus e to the 2t over e to the 4t plus e to the 2t plus 1 raised to the 3/2. Cool, cool? All right. Third component is going to be kind of unfriendly, sort of like our first component was. That's okay, we can do it. So we'll add a page here. Now we need to find, so our third component, instead of e to the 2t, it's just e to the 1t. So our third component, let's see, what color should we pick now? We'll do in, I guess this color. So third component. So we'll have e to the t over e to the 4t plus e to the 2t plus 1 to the 1/2. And again, we need to differentiate with respect to t. Okay. So that's going to end up being, sorry, my hand's getting tired, e to the t times e to the 4t plus e to the 2t plus 1 raised to the 1/2 minus e to the t times 1/2 e to the 4t plus e to the 2t plus 1 raised to the negative 1/2. And then using the chain rule, we'll get 4e to the 4t plus 2e to the 2t. That's going to be all over e to the 4t plus e to the 2t plus 1. Good so far? Awesome. All right, again, factoring out what we can, we'll have e to the t. We've got to factor out 1/2 e to the t, and then also e to the 4t plus e to the 2t plus 1 raised to the negative 1/2. When we do that, we're going to need a 2 for the first one. We've got the e to the t, and then we're going to need the e to the 4t plus e to the 2t plus 1 raised to the 1 power to give us our positive 1/2 factor. And then minus 4e to the 4t, this quantity, plus 2e to the 2t. And I think we took care of everything else. And that's all over e to the 4t plus e to the 2t plus 1. Getting there. This will equal to e to the t times 2e to the 4t plus 2e to the 2t plus 2 minus 4e to the 4t minus 2e to the 2t. All over 2 times quantity e to the 4t plus e to the 2t plus 1 raised to the 3/2. So we will have e to the t, and let's see, this time the 2e to the 2t zero out, right? We'll be able to factor out a 2, and we'll have quantity 1 minus 2e to the 4t, as long as I didn't make a mistake, over 2 e to the 4t plus e to the 2t plus 1 raised to the 3/2. And then at the end of the day, we will get e to the t times 1 minus 2e to the 4t over quantity e to the 4t plus e to the 2t plus 1 raised to the 3/2. We found out that t prime at t is equal to, in component form, so the very first one we had found was the pink. So e to the 2t, so it was e to the 2t times e to the 4t plus 2 over e to the 4t Actually, you know what? Let's factor that out. Well, I'll just keep it in. E to the 4t plus e to the 2t plus 1 to the 3 halves. So that was the first component we found. The second one that we found was the green one. So we had 2e to the 4t, let me find it, plus e to the 2t. And I could have factored out an e to the t from that, actually, to make it prettier. I probably should. You know what? Let's do that. If I factor out an e to the t from that, or an e to the 2t rather, I'm going to end up getting 2e to the 2t plus 1. And that's over that same denominator, e to the 4t plus e to the 2t plus 1 raised to the 3 halves. And then our last part ended up being, we did that in this color. So what did we get? We got e to the t times 1 minus 2e to the 4t all over that same denominator, which was e to the 4t plus e to the 2t plus 1 raised to the 3 halves. And that's our t prime at t. Well, why don't we find t prime at 0? So wherever there is a t, gonna plug in a 0, all right? And so that's gonna give us a bunch of e to the zeros, all right? So we're gonna end up with this. So we'll have 1 times 1 plus 2 over 1 plus 1 plus 1 to the 3 halves. And that denominator will be the same for all of them, right? For the next one, we'll have 1 times 2 times 1 is 2 plus 1. This is 3 to the 3 halves. And then 1 times 1 minus 2 over 3 to the 3 halves. Cool so far? So t prime at 0 will be equal to 3 over 3 to the 3 halves, comma, 3 over 3 to the 3 halves, comma, negative 1 over 3 to the 3 halves. Now, 3 to the 1 divided by 3 to the 3 halves will be 1 over root 3, right? Or root 3 over 3, however you want to do that. So I'm just going to write this as 1 over root 3, 1 over root 3, and this one is negative 1 over root 3. Cool so far? All right. Now, what is the magnitude of this? So the magnitude of t prime at 0, we're almost there, is going to be, we're going to square each of those, right? And add them. So we're going to have the square root of a third plus a third plus a ninth. Cool so far? Okay, and so the magnitude, so that gives us that the magnitude of t prime, sorry, these are vectors, at 0 is equal to, what do we get? 2/3 plus 1/9, so that would be 6/9, 7/9. So we have the square root of 7/9 And so the magnitude of t prime at 0 is going to be root 7 over 3. And that gives us that n at 0 will be the vector t prime at 0 over the magnitude of t prime at 0, which is 3 over root 7, I'm inverting and multiplying, times 1 over root 3, 1 over root 3, and then negative 1 over 3 root 3. And so here we go, I'll magnify it for you. So this here is this guy. We now need to find our AT and our AN, right? So we found T at 0, we found N at 0. So A sub T, remember at T equal to 0, we'll get A sub T is equal to the acceleration vector at 0 dot T at 0. Now the acceleration vector at 0, remember, is going to be r double prime at 0, right? So did we ever find r double prime? No. So let's find r double prime. So that's going to be r double prime at 0 dot rt at 0. R double prime is going to be, let's see, r prime was, so we'll get e to the t and then positive e to the negative t 0. So actually I'll go over here, r double prime at t was equal to e to the t, e to the negative t, and e to the 0. And 0. Just double checking. Yep. Okay, and so r double prime at 0 therefore will be 1 over 1, which is 1, 0. So 1, 1, 0 dot t at 0. So t at 0 was way over here. 1, negative 1, 1 over root 3. 1, negative 1, 1 over root 3. So we're going to end up getting, not a vector, we're going to get 1 over root 3 plus negative 1 over root 3 plus 0, which is just 0. So that's our a sub t. Our a sub n will be, remember that was a at 0 dot n at 0. So we found that a at 0 was 1, 1, 0 dot n at 0 was a little messier. 3 over root 7 times 1 over root 3, 1 over root 3, and negative 1 over 3 root 3. So then, let's see, we will get 3 over root 21 plus 3 over root 21 minus 1 over plus 0. So that's going to give us 6 over root 21. Okay. And if that's too messy for you, you could multiply it by, you could rationalize it, root 21 over root 21, and that would give us 6 root 21 over 21. You could divide out a 3, and we would end up getting root 21 over 7. Sorry, 2 root 21 over 7. And oh my gosh, we are done with that problem. Woo! All right, so I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Bye.